Hello everybody, in this lecture we will be going over 2017 IMO problem number 5. Here is a view of this combinatorial problem. An integer n is given and a collection of n times n plus 1 soccer players, no two of whom are of the same height, stand in a row, and Sir Alex wants to remove a certain number of them such that 2n players will remain in that row. Notice that the soccer plays in that row initially are just randomly ordered in terms of their heights. So you can think of it like a mountain range, if you will. And we would like that after we remove these n times n minus 1 players, we would like to have these conditions met, namely that no one stands between the two tallest players remaining among those 2n people, no one stands between the third and the fourth tallest player, and so on. No one stands between the two shortest players after those people have been removed, because at the beginning it's like a mountain range. Obviously these conditions will not hold. So in this video I would like to provide an idea for an algorithm that obviously works, but I will just provide a sketch of the proof and I will leave the details of the proof to you guys. Mainly I would like to show it on an example. Let's first build an example for n is equal to 3, and then I'll work out an example for n is equal to 4. We will then discuss probably why the algorithm works and what makes it work. Probably in the case n equals 3, it's we will warm up to the idea, and then the case n equals 4, and if we have time n equals 5 as well, will give us further verification, that confirmation that our algorithm might be actually the correct one, and we will discuss what method can be applied to prove it. And obviously it turns out that probably an inductive type of argument might work. Okay, but so let's start with n is equal to 3. So we have apparently 3 times 4 equals 12 players on the bench now, in a row I should say, and those players, their heights, so because no two of those players have the same height, without loss of generality, let's say that their heights range from 1 through 12, and we would like to remove 6 people from this set. Why? Because 6 is equal to, according to this description, 3 times 3 minus 1, which is just 6, obviously, 3 times 2. So we would like to remove 6 people. Once we remove these 6 people, we would like to investigate if these conditions will be satisfied. So let me go ahead and randomly write 12 people, and then let's discuss it. So these are the numbers that I would like to randomly order. 1, say 2, 3, yeah, well, let's put 3 farther away. 3, 4, 5, 6, I don't know. Well, not say 7, 8, 9, say 10, 11, and 12. There you go. So I have hopefully the 12 numbers, and here is how I implement my algorithm. I'm first starting by splitting this into 3 groups, because n is equal to 3, and because we have n times n plus 1 players, obviously each group should contain n plus 1, in this case 4 players. So once we have these groups ready, we will use the following thing. So in each group I will identify the 2 shortest group members. In the first group, that would be these 2 people. In the second group, these 2, and in the third group, I guess 4 and 8. Now once we do that, we need to find which one is the smallest, the second smallest player in any given group. So the second smallest player is 2 here, 5 here, and 8 here. The smallest among these 3 are 2, obviously, so I will circle 2, and I will circle the other one that has been dotted, the shortest player in that group. And what I will do next is, I will just delete the people in the group where I have chosen 2 people. For the other 2 groups, I will just delete the shortest players. You might think, hey, what will that guarantee, right? So, well, in this particular example, because we have 2 consecutive numbers in the same group, it's not quite clear what we're doing, but bear with me, and probably in the second attempt we will have a better chance. Now we have chosen two players from the first group, and look at that, they are consecutive, so that's really nice. They didn't have to, but obviously in this case you can't put another number between them, so that's pretty good deal here. So then we go to the next. So we have now 2 groups remaining, and we do the same procedure. So identify the 2 shortest in both groups. So here they are. And next is which one is the smallest second element in the group. So the second shortest element is 7 here and 9 here. 7 is less than 9, so therefore I will circle 7 and the other number from that set, and what I will do is I will remove the remaining element of that set, and when we go to the other set I will just cancel out the smallest element in that set, which was 8. So therefore we have chosen also 5 and 7 here. There is the risk of running 6 here, but luckily our procedure eliminates that risk. And finally, we have 9 and 11. I will just pick the remaining 2, and boom. Wow. So therefore, look at the remaining people. So we have, let me rewrite the sequence now. The reduced sequence as a result will be 2, 1, as I write from left to right, 7, 5, 9, and 11. As we said earlier, this is the smallest 2. The medium 2, well, it happened to be that in block wise they are increasing, but it didn't have to be that way. But wow, so this obviously satisfies the conditions of the problem. So I have a couple of things. So let's work it out slightly different. I don't want 1 and 2 to be on the same group, so let me just slightly change this thing, and then let's see if this result will still hold. So let me start with 2, 6, 12 again, but let's put the 1 elsewhere. So probably, for instance, let me bring in I don't know, say 5 from this group. So let's switch the position of 7 as a 1 and 5 actually. 10 and 3, and the rest of the elements, let me not make any change. Let's quickly apply our algorithm again and see if algorithm still works, and try to see if we can have some intuition behind it. So this is a new example. Again, n is equal to 3 here, but I have reordered the people in a row and see if it can still work. So therefore, again, identify the shortest 2 people in any given group. 4 and 8 here. Obviously, the second shortest, well, when you concentrate on the second shortest group in every set, like 5 here, 3 here, and 8 here, the smallest among these is 3. So I'm circling 3, I keep the 3, I keep the 1, and then first of all I delete these people. That's okay, but what's more important is I delete the shortest people in the other groups. So what will that ensure? That will ensure that any number in between them are likely to be the shortest number in the other sets, and it can't be a second shortest number in the other set yet can be inside this, because 3 is the shortest among all the second shortest people, right? So therefore, by eliminating 2 and 4, these are the likely people that can go between 1 and 3, and I have eliminated this possibility now. Now the rest of the thing is, now that I have chosen 2 people here and eliminated all the other members in this, I'm kind of building an inductive argument here. So we started with n sets, now we are reduced to n minus 1 remaining sets. Well, in this case 2 remaining sets, the first one here and the second one here. So this set altogether has been eliminated in the second round, right? So now when we redo the second round, 5 and 6 are the smallest guys here, 8 and 9 here. When you compare the smallest of these two, 6 versus 9, 6 is the shortest. So therefore I will highlight the 6, highlight the shortest in that group, and eliminate the 12. Among these two, make sure you eliminate the shortest, keep the other two, but then and minus 1 2 here in this case we did here. So 5 and 6 remain, right? But that's beautiful. And then because there's no more, so we have one more step to go, but there's only one set left, and it's the last one, and in that one there's only two elements. So when you list the remaining guys, the remaining elements, I think by now it should be clear what we've been doing, right? 6 3 1 1 3 9 and 11, and boom, exactly, right? So what are the shortest two people? These two, and obviously there's no number between them, right? So that's perfect. And then the second, the shortest people are 5 and 6, and finally 9 and 11, and boom. So it is such that there is nobody in between them that would kind of, so for instance 1 and 3 are the shortest, so you can't have slip a 5 because so that wouldn't satisfy the conditions of the problem. So no one stands between the two tallest players remaining, and obviously the two tallest players remaining are 9 and 11, and no one is standing between them, right? And that's perfect. And that's kind of the algorithm. So the key fact of the algorithm, let's repeat this one more time, and actually let me do it on one more example. This time let's try n equals 4, because there are so many numbers involved. It might be smart for me just to make sure that I'm not missing any point here. So first of all, I have these 4 sets. I need to arrange the numbers in those 4 sets such that 5 numbers in each set. So right, so let me quickly do the splitting here. Okay, and now let's put down some numbers randomly, hopefully as random as it gets. Obviously, how can you do it randomly, right? So even computers cannot generate random numbers. Who am I to do that? But I'll try. So 7, I don't know, 8 maybe, 9, 10, 11, why not 12, 13, 14, 15, I don't know, 16, why not 17, 18, 19, where the hell is 20? Here it is. And if you guys are ready, you can pause the video here and try it for yourself. But assuming that you did already pause, let me go ahead and show how to build up. So in the first step, we have 4 sets. So number of sets is 4. And from each set, I will first identify the two smallest numbers, 1 and 4 in the first set. I assume 3 and 7 in the second set. Second block, probably I should say, 2 and 8. And finally 5 and 6. So when I compare these smallest guys, we focus on the shortest one, like the second shortest in each group. 7, 8, and 6. Which one is the smallest among these? Well, 4 looks like 4. So keep the 4, keep the 1, eliminate everybody else. That's good. But what I do also, which is critical here, is I eliminate the smallest guys in the other blocks, right? So what would that ensure me? Notice that 2 and 3 are eliminated here. These are the two people that can go between 1 and 4, and I eliminated them in the thanks to my procedure, right? So there is no other element that can go between 1 and 4, because any other element, let's say 7 for example, is the second smallest in that group, shortest in that group, but there's no way it can go inside this guy, because between 1 and 4, because this is the way we have chosen 4, right? This is the shortest second element in any given group, and boom. Now, why did I eliminate everybody else in the first group? Because I have already chosen 2 people from the first set. Recall that at the end, finally, we will have 2 n people standing, right? Because I have n groups, the first block, the second block, third block, fourth block, or maybe in this case n is equal to 4, obviously. By choosing 2 people from each block, I'm done, right? So that's as simple as that. And now I can repeat it inductively. So we have done in the first case. Now in the second case, we will keep repeating this. So each time we will have one last block, and because I have a finite number of them, eventually this procedure, this algorithm needs to stop, right? And you need to clearly explain it in your proof writing part. Okay, let me just for completeness sake, let me finish this this example. Now let's just delete these arrows. Okay, so what are the remaining shortest two people in each group? So we have now group 1 is eliminated, block 1, we have block 2, 3, 4. We have already chosen two people from block 1. This is just great. So our sequence will start at 4 as 4, 1, 9. The two shortest are 7 and 11. The two shortest here are 8 and 12, and then 6 and 13. Now when you compare the second shortest in each set, so it would be 11 here, 12 here, and 13 here. Obviously the smallest among these is 11. Keep 11, keep 7, but make sure to eliminate the contestants from the two other contestants from the other sets, the shortest ones. In that case, obviously that would be 6, and here it would be 8. And true enough, 6 and 8 were potential people which would have been between 7 and 11, but we have eliminated them, right? So by eliminating them, I'm ensuring that the next two, so these two will be kind of, in that sense, there will be no other height taller or smaller between them, right? Okay, so eliminate the others. So you have 11 and 7 that carries, so this block is eliminated as well. Two remaining blocks, 12 and, so therefore let's get rid of this. Oh, come on. Okay, so 12 and what is it, 15 are the two shortest, and then 13 and 14. The shortest among these, second shortest among these, comparing 14 and 15, I realize 14 is the shortest, so I'm going to pick 14 and 13, get rid of the 20 here, just get rid of the smallest here, and boom, we're done. So from this one we have 14 and 13, don't change the order, 15 and so this group is gone. In this one there's only 2 left, so the procedure completes here, right? And look at this list. So let's see if the condition of the problem is satisfied. So no one stands between the two tallest players. The two tallest players in this range of 8 people, 4 times 2 is equal to 8, are 15 and 19. Boom, there's no one between them. Perfect. Who are the two second tallest? 13 and 14. No one standing between them. The following two are 11 and 7, works. 4 and 1 works. And we're pretty confident about our reasoning. We have done a few examples, it works. And just to summarize one more time, by choosing the second smallest in each block, so first I split it into n blocks. I will pick 2 numbers from each block because my goal is to have 2 n people remaining. Everybody else needs to go, and the way I do it is identify the 2 shortest people in each group. Once you identify the 2 shortest people in each group, make sure to identify the shortest second member of each group, right? So, and just eliminate the shortest people in the other groups, because they have the chance to go between those 1 and 4 in this particular example, and that might cause problems. Of course, when you formalize this, now the hard part begins. You have about 1 hour to, after doing a 30-minute example, working out the example, a case work as usual for any Olympiad problem, that always is a good idea. The hard part begins, and you need to somehow formalize all this, explain it very well in your writing, explain it to the judges, so make sure there's no confusion. Obviously I didn't work it out very nicely, so I don't want to go over how to write it clearly, but the main idea is here. This algorithm is one of the algorithms that work. Obviously you can check AOPS to see if there are some other algorithms that that might work as well. So the AOPS discussion forums are pretty good for that reason as well. So hope you enjoyed the video, and looking forward to see you guys in our next lecture.